Right, we're going to make a graph of temperature over time, and we're going to add energy to something. And let's say that we're going to start with, we'll just say like 18 grams of ice. And let's have this 18 grams of ice start out at negative 10 degrees. So let's call this like negative 10. And this is where it starts. We'll say we have a thermometer embedded in the, frozen in the very cold ice. And if I put it in a beaker and I start a Bunsen burner underneath it, I'm going to be adding energy to it. And you might realize that if we graph that, then you would think that the particles in the ice cube would start moving faster, and so therefore the ice cube would start to warm up. But what you might not realize is that it only warms up to a certain point. Something special happens at 0 degrees Celsius. And you know that ice will tend to melt at that point. Now, it's unusual here because we keep putting energy in, but the temperature will not continue to go up. The temperature will actually plateau. But we're still putting energy in. What that means is that the energy must be being used for something different than to raise the temperature. We need to kind of have a grasp of what exactly temperature is. Temperature is really a measure of the kinetic energy of the particles. So if the energy is being put in to make the particles move faster and faster and faster, then you would see that show up in a temperature change. But if the energy is being used to do something else, like not speed up the particles, then you wouldn't see that in a temperature change. A lot of times I think students think of temperature change and energy as the exact same thing, and they're not. Temperature sometimes manifests itself. It shows that there is energy being put in, but just because there's not a temperature change, if there's not a temperature change, then that doesn't mean that the energy is still not being put in. In this case, the energy is being put in along this plateau here, and the energy is being used to melt the ice. So that takes a little bit different energy to do that. So we're going to take our ice molecules, which are kind of shaking, vibrating together, and we're going to separate them and turn them into liquid flowing molecules past each other. And so while that's happening, no change in temperature happens. So we have an interesting couple points. Right here we would have 0 degree ice. It'd all be solid. But here we would have 0 degree water. It's the exact same temperature, but they're different states. So in this plateau line, we have an ice-water mix. If you're going to the right, which kind of put some directions on it, if we're going to the right this way, then that's called a positive heat flow direction. We're putting heat into the system. Of course, if you're going back the other way, then that would be a negative heat flow. Heat would come out of the system. So if I went from this dot to this dot, heat comes out of the system. We go from 0 degree water to 0 degree ice, and it's called freezing. If we go from ice to the liquid, then of course that's called melting. So it's important to realize that when we have state changes, we have no change in temperature. Now, as soon as the very last little bit of ice, if you're watching it, melts, then all of a sudden you'll see the temperature start to go up again, because now we're all in one state called liquid, and the particles are again moving faster and faster and faster and faster. So you'll start seeing a temperature increase again, and that'll of course only go up to a certain point, which generally is around 100 degrees for water. Now this could be something other kind of substance, and the boiling and freezing points would be something different. But for water, is what we're concerned with right now. At this point, a new state change begins called vaporization. And so we have another plateau. Now this plateau is longer than the first plateau. It actually takes quite a bit more energy to boil the water than it does to melt the ice. And that's because, again, the energy is being used to break the interactions of, if you will, of liquid molecules, but also then to spread them apart. Gas has space between it, so it takes a little bit more energy to do that. But you'll notice the energy is being used to change the state, not to increase the temperature. And then, of course, right here we would have 100 degree steam. And then once it's all in one phase again, the temperature of the steam could keep on going up. So whenever we have a steam liquid mix, we're going to be at like around 100 degrees, and whenever we have solid liquid mix, we're going to be around 0 degrees. And these are state changes, and we're not going to have any temperature changes. Now let's say I want to figure out the energy that it takes to do this entire thing. Well, there's two equations that we actually know for energy. There's energy when we have temperature change, and we multiply three things together. We multiply the mass of the stuff times the specific heat constant of the stuff times the delta T, the change in temperature of the stuff. So if you look on here, what points, or what lines, I guess I should say, would we use MCAT to figure out how much energy is being put into the system? Well, we would use it here, we'd use it here, and we'd use it here. Any time where you see a change in temperature, the way to figure out the energy being put in is to use MCAT. Now, there's another equation that we use to find energy when we don't have a change in temperature, but we're doing something to the substance. And that one we've talked about is Na, N times heat of, and then something. Usually we have a little subscript there of what we're doing to something. We've already talked about heat of combustion and heat of solution in class. Today we're going to talk about heat of various state changes. You'll notice both these equations are actually similar. There's an M in the first one and an N in the second one. Both of those are dealing with matter. M is grams of matter, though, and N is moles of matter. But we can convert back and forth between those depending on which equation we're using. The other thing to remember is that MCAT, this one, is the units are going to be in joules if our specific heat constant C is in joules per gram degree Celsius. And our other one is going to be in kilojoules. So to add them all together eventually, it'd be probably pretty good to take your MCAT and divide by 1,000. If you divide your MCAT by 1,000, then that will be in kilojoules also, and then you'll just be able to add everything else up. So what that means is to figure out the energy going in here and here, we obviously can't use MCAT because there's no change in temperature, so that wouldn't help us. But we can use Na. We can take the moles of the water and multiply it by the heat of and whatever it is. So if we're going from here to here, that one is called the heat delta H of vaporization. I'll label it VAP, the heat of vaporization. And for water, that is 40.7 kilojoules per mole. Kilojoules per mole. So it takes 40.7 kilojoules to vaporize a mole of water, which would be 18 grams of, or 18 milliliters of water. That's how much energy it takes. And so these heats of water you need to probably remember. So then going back the other way from here to here, we would just have something called the heat of, and this state change is called condensation. So the heat of condensation, and of course it'd be the same number, but it would be negative 40.7 kilojoules per mole. So to vaporize, it takes 40.7 kilojoules per mole of water. To condense it, you'd have to take away 40.7 kilojoules per mole of water. And then down here we have some that are a little different. This one on the bottom, to go from here to here, that's called the heat of solidification. The heat of solidification. And it's negative 6.01 kilojoules per mole. And then, of course, to melt it, you would think we'd call it the heat of melting, but we don't. We make it a little confusing. It's called the heat of fusion. The heat of fusion. And it's 6.01 kilojoules per mole. So really there's only two more constants to memorize here. But it's just positive or negative depending on which way we're going. If we're going to the right, we're talking about positive energy. If we're going to the left, we're talking about negative energy. And the amount of heat to melt a mole of ice is around 6 kilojoules. And the amount of heat to boil a mole of water is around 40.7 kilojoules. You'll notice it takes about 6 to 7 times more amount of energy to boil something than it does to melt something. So all we need to do to figure out the energy for this whole thing is just to solve all the little problems. And we have here and here on the plateaus, we'll be using Na, the moles times the heat of vaporization or the heat of fusion, depending on which one we're doing. And then to figure out all these inclines, we would use MCAT. And of course, we divide MCAT by 1,000 every time, so that both these would be in kilojoules. And we'd add up all 5 amounts of energy to figure out how much there is. Okay, and we have 2 practice problems in your book, so hopefully you might want to do those and to practice this out. But let's go ahead and let's do a little practice problem. See if we can figure this out. Whoops, I was on the wrong page the whole time. Okay, so I'll do this backwards. You'll notice I have a question up here, which I wanted to be on my second page, but I guess I didn't realize I had done that. So the question is, how much energy does it take to convert -10 degrees ice into 120 degrees steam? So let's go back. I guess I do have another graph here. We can use this one. So let's kind of figure this out here. So let's start down here at this point. And we'll say this is -10 degree ice. And we're going to, of course, warm it up to 0. And then, of course, we're going to have to melt it. And then we're going to, let's just melt it all the way over. And then let's warm that up. That'd be to 100. And then we're going to boil it. And then we're going to heat it on up to, what I say, 120. Okay, so we got several MCATs that we're going to use. We'd MCAT it here, here, and here. And so if we do that, the energy here, let's see, what was this? This was 180 grams of ice, right? Let's go back. How much does it take to convert -10 degree ice into 120 degree steam? I guess I never put on how much it was. Okay, let's say that it's 180 grams of ice. Okay, so I'll write that up here. 180 grams of ice. Okay, so we're going to MCAT it in 3 different places. So for right here, I'll move this one all the way over here. That would be mass, which would be 180, times the specific heat of what? Well, a lot of times you might say 4.184, but this is not actually water. It's ice. And even though it's the same formula, they have different specific heats depending on the state. So if you look it up in your book, you'll see the specific heat of ice is around 2.11. So you need the specific heat of whatever it is you're warming up. And of course, that's in joules per gram degrees Celsius. And the gram in degrees Celsius, of course, will cancel out here a little bit. So the change in temperature is -10 up to 0, so that's 10 degrees. And then we would divide that by 1,000. And if we do that, we'll figure out how much energy that is. That should be around like we'll round it off, 3.8 kilojoules. So that's how much energy it takes to warm up -10 degree ice, 180 grams of -10 degree ice up to 0. Okay, so let's look at this MCAT right here. So what do we got? We have 180 times, and of course this is the specific heat of water, 4.184. This is water. I better do parentheses. And what's the change in temperature from here to here is 100 degrees. And I'll divide that by 1,000. And if I do that, I'll get around 75.3 kilojoules. So that's how much heat it took to warm the water up. We're just doing all the MCATs right now, so we're skipping some places. For right now, we're skipping our plateaus. There's energy being put in there, but we're just ignoring it for right now. Let's look at our last MCAT up here. We have 180 grams of stuff. The mass doesn't change on any of these. It's still 180 grams. The specific heat would be, though, for steam. That's a little different. That's about 2 joules per gram degree Celsius. And then the change in temperature, 100 up to 120 would be 20 degrees Celsius. And we'll divide that by 1,000. and we'll figure out that that's around 7.2 kilojoules. Okay, so we have that amount. That's the middle MCAT, and there's the bottom MCAT. If we add those all up, we'll have energy that it takes to change the temperature all the way through this. But we need also the energy to change the states. Now, the formulas, of course, for those are Na, N moles times the heat of whatever it is. Well, the reason I chose 180 grams of ice, I think is pretty obvious. 180 divided by 18 is the molar mass of H2O, gives you 10 moles. So that's kind of nice and easy. So we're going to use N times the heat of things. It's always going to be 10 times whatever the heat of what we're doing. So what are we doing from here to here? Well, we're melting ice. So that would be, to gnaw that would be 10 moles times the heat of melting, or the heat of fusion, which of course would be 6.01 kilojoules per mole. The moles, of course, would cancel out, and I would get just kilojoules. So this is going to be easy. This is going to be 60.1 kilojoules. Okay, how much energy did it take to go from here to here? Well, that's also Na. So it would be also 10 moles times, in this case, to go to here, we're vaporizing it. So it would be heat of vaporization, 40.7. And that would be 407 kilojoules. 407 kilojoules. So I have my 3 yellow boxes here of how much energy it took to MCAT, the change in temperatures. Here's how much energy it took to vaporize the liquid water. And here's how much energy it took to melt the ice. So if I take all 5 of these and add them all up, I will get, and you can check the math on this, around 554 kilojoules of heat or energy it took to do all of that. That's kind of like a 5-step problem there. Some of the problems won't be that hard. I might just say that you have, maybe you'll start right here. You'll have 100-degree water, right there, 100-degree water, and I'll say turn it into 120-degree steam. So all you'd have to do would be to vaporize the water and then heat the water up to 120 degrees. So it'd only be really 2 steps. You do a Na here, and then you do an MCAT there in kilojoules and add them together. So hopefully that'll help you with some of the problems on your E-Lab on how to do various state changes.